Hello everyone. Homeowners these days have several tasks that require the use of heavy machinery. If you want to clean up your lawn, you're going to need a good landscaping equipment. If you have a concrete patio and if you don't like it anymore, you're going to need a heavy-duty jackhammer. But did you also wish that these things required less effort and costed less? That is where our concrete breaker comes into play. My name is Kush Patel and I'm the mechanical design and programming lead for our team residential concrete breaker capstone project. I'm also the primary contact between the sponsor and the team. Our team sponsor is Dr. Faryar Adesami and the faculty advisor is Dr. Hormuz. My team members include
Hi, this is Fadi Shahin and I'm in charge of design analysis and CAD modeling.
My name is Alysa Velez and I'm the electronics and prototyping person.
Hi, my name is Abdulaziz AlJaber and I'm in charge of cost analysis and sourcing of parts.
Hi, my name is Mike Iliesi. I helped with calculations, prototype design, and final review of the presentation and the report.
My name is AbulRahman Baalharith. I help the team for scheduling meetings and prototype design.
Thank you.
There are three reasons of why we should care to design a new concrete breaker. The normal concrete breaker that is in the stores now costs a lot of money to own one of them. Also, you need to be professional in using the concrete breaker so you do not get injured. Special clothes and gloves need to be on to be safe with using the normal concrete breaker. Thus, a new concrete breaker design that is easy to move, automatic, and more affordable than the available design need to be created to meet customer needs. The most important customer needs are affordable, break 4 inches of concrete, safe to use, under 1 minute cycle operation, remote operation, automatic, easy to assemble, disassemble, and move. The group came up with the 9 prototype and they narrowed it to 4 prototype by analysis. You will see it in the following slides. So the 9 prototypes are engine pistons, tensile spring, clutch mechanism, drop hammer, sliding hammer, spoon hammer, guillotine hammer, power hammer, and 3D printer concept.
This is our customer requirement versus engineering requirement matrix. The customer requirements that AbulRahman previously mentioned have driven the engineering requirements we deem essential to bring the customer's idea to reality. In order for the concrete breaker to be portable, we intend to keep the design simple as to be quickly assembled by the user. Our design must be able to break 4-inch slabs of concrete and will need to be built with robust materials. Creating an automated system meets the customer needs of a product that is safe to use through remote operation and will impact the concrete in cyclic intervals.
One of the requirements for this project was keeping the price of production below a certain price point. This price point at first glance seemed very low for what we needed to design. After brainstorming a few possibilities, we concluded that at the budget given, we will not have enough for a design that can break concrete while meeting the remaining requirements. After further research, we found that attaching a motor will be necessary as well as keep us on the low end for a budget. Another caveat we ran into was making the design portable as per the requirements. For this, we thought about adding wheels to the design itself, but figured that it may cause stability concerns. So, we decided on making our design with the capability of easily setting up and breaking down, but leaving the mobility for further research.
From our 9 prototypes, a selection criteria matrix was utilized to narrow down the options to 4 final designs. The first one was the tensile spring trimmer, the sliding hammer, the drop hammer, and the power hammer. We will now demonstrate the theory and principles of operation for each prototype.
Design 1 was a fusion of 2 design ideas from different team members. One of them worked on increasing the impact energy of the design while maintaining its compactness, while the other worked on having a more efficient mechanism. Springs were added to increase the impact energy of the chisel whilst having a lower height. the addition of springs also help to maintain the height and not have a very tall design. The drivetrain mechanism was heavily based on how a trimmer works. The sketch displays how a force cycle would help lift the support. This animation shows how both the designs were implemented and combined to achieve a final model that would meet the customer requirements whilst maintaining simplicity. Now, some other design ideas will be discussed by Fadi, Shahin and Michael Iliesi in the next phase of this video.
Our biggest struggle with designing the concrete breaker was the budget we were given by our sponsor. And this design was equated by using parts that can be purchased and found for a cheap price from retailers or the internet. These parts are a sledgehammer, a small motor that is powerful enough to lift the hammer up, a chisel, springs, and steel bars. The assembly for this product should be easy and will not take time. This machine should work by lifting the hammer up to a certain height by an arm that is connected to a wheel that rotates by the motor, and they are all placed on an angle. After the arm lifts the hammer up to a certain height, it will get out of the way because of the angle where it loses contact with the hammer arm, and then the hammer will drop down on the chisel using gravity and a spring that is connected to the bottom of the machine. The chisel will be able to break the concrete with the impact of the hammer when it drops on it. The arm will rotate again and lift the hammer up, and there will be a spring to lift the chisel back up every time. The process will repeat and do these steps over and over while the motor is still turned on. Thank you.
This is another variation of the drop hammer shown before. However, the lifter mechanism is an oblong cam wheel which lifts the hammer arm as it is rotated by an AC motor. When close to 1 revolution is reached, the flat part of the cam allows the arm to drop, taking careful note that the hammer should impact prior to the cam wheel making contact with the arm again. The hammer then drops onto the chisel, compressing the suspension spring and allowing the chisel to puncture the concrete with the full impact force of the hammer. The cam continues to turn, and to lift the hammer arm again for a repeated cycle. Springs are placed to the left end of the arm in order to maintain positive tension of the hammer arm with the cam wheel to prevent bouncing and excessive vibration. This prototype incorporates a sliding hammer design. The inspiration comes from a commonly used mechanic tool used to pull bolts, shafts, and various other components. These can be located in difficult to reach locations or leveraged in spaces not adequate for room to extract. The tool is also used to insert components to locations where there is a larger resistance due to interference type fits. For example, a small 5-pound weight slides over a guided shaft which is attached to the component. Through rapid acceleration by the operator, a sharp, forceful impact is applied to the component, thereby manipulating the applied kinetic energy by several factors when compared to ordinary pulling and pushing methods. The sliding hammer concrete breaker operates with the same ideas. However, several modifications have been made to increase capacities and impact forces. Where the impact hammer usually is on the outside of the shaft, this design places the hammer within a guided shaft. 2 rods on each side of the hammer protrude through the guided shaft to enable lifting of the hammer to a suitable height. Weights can be added to the top of the hammer to increase impact energy. Chisel tips can be changed at the bottom of the hammer via threaded shafts to select appropriate impact profiles. With a 20 kilogram hammer lifted to 2 meters and a chisel tip measuring about 0.5 centimeter by 3 centimeters, a pressure of about 2600 MPa can be applied to the concrete surface, theoretically breaking a 4-inch slab. Folding support legs ensure portability and total modularity. A remote operation method would ensure total safety for the end user. Due to several complications with motor placement, remote operability, and transportation options, further details and methods of operation have not been explored further for this concept.
Our team was fortunate to have ample design ideas for this project. Although there were several similarities between them, the inspiration and thought process put into them were independent. These designs will help prove that our team spent much of their time on developing different design ideas that would best suit the customer's need. To choose these final designs from a pool of other capable candidates, a selection criteria matrix was used to narrow down the best 4 candidates that were likely to be our final design. Each team member rated each design in terms of its deliverables and how likely it was to meet the customer needs.
The final design selected for future work and as a final prototype was the drop hammer. This was ranked the highest in the Pew matrix by all team members due to several factors. We felt that since price was the driving factor, this prototype would be the easiest to manufacture and keep costs low. The design also provides the most impact energy to the concrete slab and therefore is most likely to succeed. Other criteria such as automation and the safety of the end user were also important considerations when determining the final design. For customer needs and satisfaction, this prototype will also have the fastest cyclic operation, ensuring that there are minimal drawbacks to the use of this product in residential applications.
Allow me to briefly go over what we have done so far for this project. First, we met with our sponsor to receive the requirements of this project. Soon after, we brainstormed ideas to come up with preliminary designs. We then tailored our designs to not only meet the requirements, but also succeed in some aspects. Unfortunately, as we dug deeper into the concept, we concluded that the budget was too low. After more research was done, the idea of using a motor was brought up. This idea was ideal given the restrictions on pneumatic and hydraulic systems. So we reworked some of our designs by including the motor. We then used a criteria matrix to vote which design we thought best. With the help of the criteria matrix, we went from 9 designs down to only 4. These 4 designs satisfy our sponsor's needs by being portable, safe, and easy to use. But we still believe that further calculations and analysis are still needed to draw a winner of the 4 designs.
We still have to do a lot of things for next term to make sure that the concrete breaker design we came up with is going to work perfectly and can be produced easily. That will include calculations, materials used, and the assembly of the product. For calculations, we will need to figure out the impact needed to break a 4-inch concrete block and how much weight we need to drop on the chisel to break it. We will also need to figure out all the calculations to make sure the machine is reliable and won't fail over time. For the parts used for the machine, we will figure out the right materials used to make sure that the machine will be in a good quality and is portable enough for the customers to move around easily. For the assembly of the machine, we need to figure out the best tolerances used for the parts during the manufacturing processes to make sure that the production of this machine goes as easily as possible. We also need to make sure that we have the best and cheapest machining methods used to produce some of the parts that are used in the machine.